Today, hello everyone, we are trying to understand why 5. Why someone should do a semi-classical analysis of a 5-dimensional rotating black holes. And spoiler alert, I'm going to try to convince you that actually doing it in 5 dimension is easier than doing it in 4. So let's see if I manage. So first thing first, let's start from the geometry of the spacetime. So this is my metric, this is my line element. Don't look at it too much, it will haunt you. And so this is a Kerr-AdS 5-dimensional black hole in which we have psi as the fifth angular coordinate. And what I want you to take from this slide, to be honest, is not the line element itself, it's a bit the setup that we have. So first of all, since we are in 5 dimension, we don't only have one axis, one rotational axis like in 4, we have 2. And we picked the angular momentum of these 2 axes. I know it's difficult to imagine because it's 5, but we picked the angular momentum of these 2 axes to be exactly the same. So we induced this enhanced symmetry in the system, which I'm going to exploit later and will make all the calculation a lot easier in what we're going to do next. And then we picked a very particular coordinate system that exploits a lot this kind of symmetry. And I should say A is the rotational parameter of my black hole, so how fast is my black hole rotating, M is the mass, and L is the length scale. So we are in ADS, so it's like working in a box. So here I have an intuitive representation of my black hole. So on the left-hand side, we can see the rotating black hole in 4D that also Mark Sals put the image in his presentation as well. So let's see the 3 surfaces. So the first one, the black one, is the event horizon, is the surface of my black hole, of a black hole. The stationary limit surface is the surface inside which an observer cannot stay at rest relative to infinity anymore. And the light surface is RJ, is the surface for which an observer has the same angular velocity as the event horizon if they are moving at the speed of light. And this surface is what we are going to focus on, because we can see here that the main difference is exactly that, is that the light surface in 4D has this weird shape that is radial dependent, while in 5 dimension, in this setup that we have this shell structure for all the characteristic surfaces. So it's like having different spheres, basically, constructing my black hole. And this makes the analysis in 5 dimensions so much easier to do. But why we want to focus on the light surface? Because we heard before that actually what we want is to define time-like Killing vector, which is time-like everywhere outside the event horizon. And we can do this only if we work in a regime in which the light surface doesn't exist. And in our setup, since we have this easy structure, basically geometrical structure, is it possible to find a regime in which this surface doesn't exist, but the black hole still exists? So still the event horizon and the stationary limit surface do exist. So here a bit of motivation now. So in the past, there have been some studies about rotational black holes, BTZ, Kerr-AdS, and there is like this weird, well, not weird, there is this relationship between the existence of the Hartle-Hawking state and the not existence of a light surface. It's not a theorem, it's not nothing, but is for each case, this relationship works. So this was mainly a hunch. We would like to understand if in 5D ADS this works as well. So if we don't have a light surface, can we build a Hartle-Hawking state? So the Hartle-Hawking state, we heard it before, but it's a quantum state, which is a thermal state, and is the one we are going to try to build to do then, you know, the whole QFT prescription. So try to evaluate observables. So it's the quantum state that we are going to use. And for the AdS, we have this sometimes. That means basically if my black hole is rotating not too fast, then the light surface doesn't exist and the Hartle-Hawking state can be built. So we're going to try to check if this works in 5 or no. Yes, so here I have 2 plots of the 3 surfaces. So the event horizon RH, the stationary limit surface RS, and the light surface RJ. On the left-hand side, I have plotted RJ again, in function of A, so the rotation, the rotational parameter of my black hole, so how fast my black hole is rotating. And we can see that it has 2 vertical asymptotes, so one in A max and one in A min. And we are going to try to work here. So between 0 and A min, there is a regime in which the light surface doesn't exist, but the other 2 surfaces do exist. So the event horizon and the stationary limit surface. On the right-hand side, I plotted all 3 characteristic surfaces. And we can also see here a bit the shell structure. So we have light surface, stationary limit surface, event horizon. So we can see this division till a point in which basically the black hole is rotating so fast we are approaching the extremal case. So the light surface is basically closing up on the event horizon. But so does this answer the question why 5? Kinda. So we answered this question saying that it's indeed easier because we saw that the geometry of the spacetime is easier to deal with. But are we done? Is that it? Well, absolutely not, because what we want to do now is QFT on curved spacetime. So we want to apply this theory and we want to study a field on this curved background. So we picked this scalar field just because it's the easiest one that we can study. And so we're left with the goal of solving the Klein-Gordon equations. So this is the Klein-Gordon equation on my curved background. And first of all, what we can do, since the symmetry of my black hole, we have that the field is separable. We can split it in this form between angular part and radial part. So here omega is the frequency of the field, m and p are the 2 parameters that will then be related to the quantum numbers, and they are associated with phi and psi. And we can put this form inside the Klein-Gordon equation and we can solve it. And what we found is 2 differential equations, one angular, one radial, and we can solve both of them. And we found out that basically the angular part is a spin-weighted spherical harmonic, while the radial part is a Hoyne function, which are both known solutions. Here a bit more in detail. So we have the angular part, that the first one up there is the differential equation for the angular part. Lambda is the eigenvalue. And as I said, the solution of this is the spin-weighted spherical harmonic with all the quantum numbers here. The radial part was a bit tougher. We had to do a bit of manipulation. We had to change a bit of coordinate, but we managed, and we put this in the form of a Hoyne differential equation, which has a known solution, which is the Hoyne function. Here Z is defined like this, and RH and R0 are roots of G. And G is a characteristic function of the line element, is the coefficient of dr squared. Okay, another thing that we can do though, so we solved our Klein-Gordon equation, right? We had the separable field, we put it in, we found the solution for the angular and the radial part. What we can also do though, is to put the radial part in this form, which is a Schrödinger-like equation, and using the tortoise coordinate r star. And what is important about this, it's that we can study the potential of the radial part of the Klein-Gordon equation. So we can start the asymptotic limit of the potential looking at r going to infinity. And we find that the potential is assuming this form, which can you see for r going to infinity is a bit problematic, But this is also because we will need to impose some boundary condition to our system. Remember, we are studying Kerr-AdS 5 dimensions, so we are in a box basically. We have to impose some boundary condition. And the other side, we have the limit for the radial coordinate going to the event horizon, and we find that the potential gives us a constant basically, depending on omega, which is the frequency. And we can define this omega tilde that is going to be useful for the quantization procedure. It's going to be one of our quantum numbers. And indeed, canonical quantization. So we heard before a bit about how to apply the canonical quantization, but main points here. So in our setup, we don't have a light surface because we're working in this regime in which the black hole is not rotating that fast, so we don't have a light surface. So we have a time-like Killing vector everywhere outside the event horizon. So we can find positive and negative frequencies. We can define them. So we can apply the theory of QFT on curved spacetime, and we can do the canonical quantization. And as we heard so many times, there is an ambiguity in defining a vacuum state in curved spacetimes. And we are going to define two. The Bolower state, which is the state defined with respect to these Schwarzschild-like coordinates, which is basically T. And the Hartle-Hawking state we saw before is defined within respect to the Kruskal coordinates. So first of all, we can apply the canonical quantization. We have a proper definition of time. We can split between positive and negative frequencies. We quantize our field. So we quantize it within the modes, and we define the an A dagger operator, which are the annihilation and creation operator respectively. Then with the annihilation operator, we define what a Bolower state is on the spacetime. And we have it P here. Remembering omega tilde is this frequency here defined. But we can do exactly the same thing with Hartle-Hawking state. We can apply the canonical quantization procedure. So the Hartle-Hawking state is a bit different. So we have different coordinates and it's a thermal state. But what we get is that we have a slightly different form. We can define those same annihilation and creation operator, B and B dagger. And we, in the same exact way, we can split it between positive and negative frequencies and define the Hartle-Hawking state. So we built two quantum states over this curved spacetime. What do we do with this? We want to evaluate observables. So we actually want to take the expectation value of something. We built the states, but we want to evaluate something, right? And the first thing that we could evaluate is the easiest one we can do is the vacuum polarization, where we are using a trick that was already introduced before, in which basically we are defining the difference between expectation values of vacuum polarization. So we define the vacuum polarization for the Hartle-Hawking state minus the one for the Bolower state. And what we obtain is a quantity that doesn't need renormalization. So we can already study this quantity immediately. And the trick here is that these two states are both Hadamard states. So the divergent part depends on the background and on the field. So if we subtract them, basically we get rid of all the divergences. And we can study this quantity here, in which we can see a thermal distribution here, which was expected because we were working with the Hartle-Hawking state, which is a thermal state. So everything is fine. Kappa, I didn't say this before, but kappa is the surface gravity of the event horizon. So what is the vacuum polarization? So the vacuum polarization is important to understand the behavior of the quantum field, but mainly is a first step to go to analyze the stress energy tensor. So this is our goal. We want to evaluate the expectation value of the stress energy tensor over this background, because at the end of the day, what we want to do is to study the semi-classical Einstein equation and try to solve the back reaction problem on this background. So a bit of conclusion here. What we did, so remembering the table I showed at the beginning, this is actually consistent. So if we don't have a light surface, we were able to build Hartle-Hawking state. So we maintain this relationship, obviously working in this regime between 0 and a min. And a bit of summary of what we did. So we introduced the geometry of the 5-dimensional Kerr-AdS black hole, and we analyzed the scalar field in this background. We constructed the 2 quantum states, the Bolauer and the Hartle-Hawking state on this background, and then we evaluated the vacuum polarization as a difference of these 2 vacuum states. What we want to do next will be to evaluate the stress energy tensor possibly as a difference between these 2 quantum states, and then try to numerically evaluate the stress energy tensor and the vacuum polarization. But still, what we want to do, the goal at the end, is to evaluate the renormalized stress energy tensor and use this to solve the back reaction problem of the semi-classical Einstein equation. Thank you very much for your attention.
Thank you very much, Alessandro. Questions?
Thank you very much. Could you say more about where in the extended space-time the Hartle-Hawking state and the Buller state exist as Hadamard states?
So, sorry if I understood the question correctly, is where this is Hadamard?
On the extended space-time.
Yeah. So I believe this should be Hadamard for the entire space-time outside the event horizon. So working outside, since we have this very particular geometry, it should be Hadamard outside the whole event, outside the event horizon, basically.
Thanks for the talk. I've got 2 questions. I don't know how many I can get away with.
Try one to start.
Okay, the first one is probably the quickest one. Just to understand, your answer to Y5 is because you can find a regime in the 5-dimensional case for which there's no speed of light surface.
Exactly. So,
but that's also the case for in 4D in Kerr-AdS.
4D, yes.
So why should it be better, easier in the 5D than in the 4D in the case for which there's no speed of light surface?
So, good question. So in 5 dimension, we have a couple of reasons why this is actually easier. One of them is the not existence of the light surface, but another one is possibly the one I can think of is that in odd dimension, actually dealing with the Hadamard parametrics is easier. So because we don't have the log term in the divergences for the Hadamard parametrics in odd dimension, as in the BTZ in 5, that works as well. And also, we have an additional coordinate of symmetry here. So we induce an enhanced symmetry between this angular coordinate because we have 2 axes of rotation, and we can exploit that again. So the crucial part here is that this psi and this enhanced symmetry that we induced can be exploited a lot in a lot of the calculation that we did and make the calculation actually easier.
Yeah, understand. I don't know if I get away with the second one. Yeah. So the second one, the Hartle-Hawking and the Bolauer vacua that you're defining, they are, I'm trying to understand them physically somehow. So they satisfy the symmetries of the space-time, they're regular everywhere. Am I thinking?
Well,
so Bolauer, I presume it has unresolved Cherubinski radiation. Bolauer probably has unresolved Cherubinski radiation. Okay, let's forget about this one.
Because the problem is the Bolauer, I think, is the most empty of the vacuum state, but is irregular on the event horizon. So if we want to really look closely to this, where is it? Here. The only problem that this quantity has, since we are doing this difference between these 2 quantum states, is that the Bolauer is not really well defined basically on the event horizon, while the Hartle-Hawking state is, since the cross-skull coordinate can go through basically.
And do you think of the Hartle-Hawking as having a thermal path just rotating different.
Huh?
Well, I'm not sure. Rotating at what velocity with respect to the event horizon, or and
So you're meaning like since it's thermally populated,
Yeah.
basically, how
Yeah.
is the
Yeah.
particles
Yeah.
quotes
Yeah.
rotating around the? Guess I'll have to think about this.
Okay, thanks.
So one final quick question.
No, it's not about your talk. It's like, what did you ask to the DALI 2 to obtain these pictures? I'm
yes.
very curious.
So these are basically, I didn't say this, but these are AI generated pictures. And basically I asked to depict a black hole in the style of Escher. And so these are all AI generated possibility of black holes in the style of Escher.
Okay, thank you.